Welcome to the deep dive. We know you're following the incredible progress in large language models, how they're changing everything with
Yeah,
text.
I was moving so fast.
But what if these models could really understand the visual world, as well as they get language? That's the really exciting frontier we're diving into today.
Exactly. I mean, our world isn't just words, right? It's full of images, videos.
Hmm.
For AI to really get to that next level,
Mm-hmm.
it has to make sense of all that visual stuff,
Yeah.
just as well as text.
And that brings us right to this fascinating bit of research we found. It's a paper identifier 2501.13106v3.pdf. Mm-hmm. It details some really interesting, new ways LLMs can be boosted to understand images and videos much more deeply. So our mission today is to pull out the key ideas, the innovations from this paper, and just make them clear and hopefully engaging for you.
Yeah, and what jumps out straight away is how much harder visual data is compared to text. Just think about it.
Right.
A single picture has a massive amount of information packed in, way more than a sentence.
Yeah.
And then video, with all those frames, it just explodes the complexity.
Totally. It's a completely different beast than just processing a sequence of words.
It really is. It's about understanding all the tiny details within an image and then across frames in a video.
It's like knowing a book just by the title versus actually reading every page inside,
Yeah.
right? You get so much more richness, but wow, it's a huge job.
Exactly. So the researchers here, they saw this. They knew we need better, more efficient ways for these LLMs to handle this visual flood, but without, losing the important stuff that actually gives it meaning.
And that's where their model comes in.
That's where their model comes in. It's called VideoLLaMA 3.
Yeah.
Designed specifically to tackle these challenges, to really push what these models can do with images and video together.
VideoLLaMA 3.
Okay,
Yeah.
and what's interesting is they made different versions. There's a 2 billion parameter one and a bigger 7 billion parameter one.
Parameters like
Right.
the model's processing power, sort of.
Yeah, think of it like brain power. Different sizes lets them test how well it scales up, how performance changes with more complexity.
Okay, VideoLLaMA 3, let's dig into it. What makes it tick? What are the key innovations? The paper mentions AVT, Adaptive Vision Transformer.
Right, AVT. So the crucial thing with AVT is how it improves the model's eyes, the part that actually processes the visual input, the vision encoder.
Okay.
Now, standard vision models often use something called absolute position embeddings. Think of them like fixed map coordinates for every part of the image.
Like a rigid grid.
Exactly. But that causes problems when you feed the model images or, video frames of different sizes or resolutions.
Ah, right. It's like a GPS that only works on one specific map scale.
Yeah.
Zoom in or out and it gets lost. So AVT fixes that. How?
It swaps out those fixed coordinates for something called 2D ROPE, row reposition embedding.
Okay, row P.
Think of these more like relative markers. Instead of saying this pixel is at exact spot XY, it's more like this bit is to the left and a bit above that other bit.
So it understands relationships between parts.
Precisely. This relative spatial understanding lets the model handle different resolutions much, much better. It can still grasp the important details even if the image size changes.
So the big advantage there is flexibility, right? VideoLLaMA 3 isn't stuck with just one size of visual input, much more useful in the real world.
Exactly. So AVT gives it much better eyesight, you could say, whatever the canvas size is.
Okay, the paper also says they fine-tuned this vision encoder. What did that involve?
Right, so just having AVT isn't quite enough. To make sure this improved vision works smoothly with the language part of the model, they had to train it, adapt it, using lots of different kinds of visual data.
Like what?
Well, this vision encoder adaptation used a real mix. General photos, obviously, for broad understanding, but also document images, so it learns to read text within pictures.
Oh, interesting, like reading a sign in a photo.
Yeah, or understanding a scanned document, and even seeing images that already have text in them. It's about giving the model a really diverse visual diet, to make that AVT truly effective across the board.
Okay, so AVT tackles the resolution problem,
Yeah.
but videos, they have that other huge challenge, just the sheer volume. So many frames. That must be computationally intense.
Oh, massively.
Yeah.
And that's where the second big innovation comes in. DiffFP, differential frame pruner.
DiffFP. Okay, pruning frames.
Exactly. Think about a video often, one frame looks almost identical to the next, right?
Yeah.
Very little changes sometimes.
Yeah, like someone just sitting still or a static background.
Right. Processing every single one of those nearly identical frames in full detail. It's a massive waste of computing power. DiffFP is a smart way to spot and basically skip over those redundant bits.
Make it more efficient.
Much more efficient. It focuses the computation on where the action is, on the parts of the video that are actually changing.
Okay, how does it actually decide what's redundant? How does diff key work?
It's a neat process. First, for each frame, it does a quick spatial downsampling, like making a smaller, slightly blurrier thumbnail version. That reduces the data right off the bat.
Okay, shrinks it down.
Then, and this is the clever bit, it looks at small patches, tiny little squares, within consecutive frames. And it compares the difference between a patch in one frame and the corresponding patch in the very next frame.
Ah, so if the patches are almost the same.
Bingo. If the difference in pixel values, they measure it using something called the one norm distance, is below a set threshold.
Like really, really small.
Yeah, if it's below 0.1, based on their setup, it means that patch in the second frame isn't really adding much new information. So the model just prunes it, skips it.
Does it process the redundant patch?
Exactly. The paper actually has a good diagram, figure 4, showing how this works. So by intelligently skipping these similar parts, VideoLLaMA 3 can handle videos way more efficiently.
That makes a lot of sense. It's like the model's paying attention only when something interesting happens. Very efficient. Now, you mentioned the training data earlier, but the paper goes into quite a bit of detail. Sounds like they were really careful about what data they used, not just throwing everything at it.
Absolutely. They really seem to follow a quality over quantity approach. For tuning that vision encoder, they used a real mix. Well, for general visual stuff, data sets like VL3 Sin7M short, LLaVI pre-trained 558K. But then, to really get good at documents, they use things like PDA and grades and SynthDoc.
SynthDoc, synthetic documents.
Yeah, computer-generated ones, which means they're perfectly laid out, perfectly accurate, great for training the model on clean examples.
So it's not just random pictures. It's targeted training for different kinds of visual understanding. Text in images, objects, layouts, even handwriting.
Exactly right. And they didn't stop there. For tougher stuff, like understanding messy handwriting, they used a dataset called FUNSD. And for really complex document layouts, there's one called DBE.
EDDE.
Yeah. And for charts, they use some data from chart to text, though maybe less, because charts visually share some features with documents anyway.
And what about understanding the details within an image? They mention fine-grained data.
Right. That's crucial for understanding what's where and what it looks like. They use region-captioned data descriptions for specific parts of an image from datasets like Osprey 724K, and also grounded caption data.
Grounded.
Meaning the text description is explicitly linked to a specific area in the image, usually with a bounding box. Think Flickr 30K for that. This helps the model learn not just what objects are there, but their specific attributes and precise locations.
Wow. Okay, so they really put a lot of thought into building a data set that covers all these different visual skills.
It definitely seems like it. A very well-rounded approach.
So after all this clever engineering with AVT and DiffFP and all this careful training, the big question, how well did VideoLLaMA 3 actually do? They tested it pretty hard, right?
Oh, yeah. Rigorous testing. It went up against a whole battery of standard benchmarks to really measure its abilities across different areas.
Like what sort of areas?
Well, understanding text and visuals, documents, charts, that kind of thing. They used benchmarks like ChartQA, DocVikiet, OCBunch. Also, its ability to do math reasoning, but from visual problems.
Math problems in pictures.
Exactly. Tested with things like Math Vistanominy and Math Vision Test.
Okay, and not just single images, you said. Multiple images, too.
Correct. Can it reason across several images? They use benchmarks like MMMU Pro and Blink Test for that, plus general knowledge Q&A based on images, real-world QA, GQA, that sort of thing.
And, of course, video understanding.
Definitely. General video understanding was tested with benchmarks like VideoM and MVBench.
Sounds comprehensive. Did they also test longer videos or understanding the sequence of events?
They did. That's important too. Benchmarks like MLVUDev and TempCompass were used for long video understanding and temporal reasoning, figuring out when things happen.
And how did they run these tests? Any specific settings?
Yeah, they were quite specific. They generally set the model's creativity low temperature to 0.0 to get factual answers, limited the output length. For multiple choice, they prompted it very directly. Answer with the option letter. Same for short answers. Answer with a single word or phrase.
Making sure it followed instructions.
Exactly. And for video tests, they actually let it handle way more visual information, up to 16,000 visual tokens, I think, and up to 180 frames.
Giving it more context for longer videos.
Right. And for tasks like temporal grounding, finding start and end times in a video, they used a specific prompt and then clever ways, like regular expressions, to pull out the predicted times and compare them accurately to the real answers using a metric called MIOU.
Okay, lots of detail in the paper for those who want the nitty-gritty. Tables 5, 6, 7 look like the place to go. But just generally, how did it perform? How did VideoLLaMA 3 measure up?
Broadly speaking, it did very well. Both the 2B and 7B parameter versions showed strong performance across this wide range of tasks.
Compared to other models?
Yeah, when compared against baselines of similar-sized models like Apollo, Intern VL 2.5, Quinn 2 VL, VideoLLaMA B3, often held its own or even came out ahead, especially in areas like document understanding, visual math, and general video stuff. They also compared it to bigger, more specialized models, just to see where it stands.
So, promising results on the benchmarks, but the paper also has some specific examples, right? Case studies that show what it can actually do.
Yes, and those are often the most illuminating bits. They really show the capabilities. For instance, there's one on-chart understanding figure 6.
What did it do?
It could look at a stock market chart, analyze the trends, and even suggest potential investment strategies based on what it saw.
Wow, that's beyond just reading labels. That's interpretation.
Exactly. And in the same figure, you could look at a graph comparing different AI models and talk about the trade-offs between their size, their parameters, and how well they performed. Pretty sophisticated reasoning.
Very cool. What about reading text in images, OCR, and documents?
Figure 7 shows that. There's an example where it successfully reads words off a design image, and another where it understands a warning message embedded in a picture. That's handling text in messy, real-world contexts.
Useful. And you mentioned a fun one earlier. Puppies in space.
Yes. Figure 9. It's shown this image, clearly fake, of puppies floating in a spaceship cockpit.
Right.
And VideoLLaMA 3 doesn't just describe it. It generates this whole coherent, imaginative story about their mission, looking down at Earth. It shows it can reason creatively from a visual prompt.
That's impressive. And there was one more. Unusual video.
A video of bears sitting at a picnic table, eating, like people.
Okay, that is unusual.
And VideoLLaMA 3 was able to point out the oddity. It understood not just what was their bears table, but that this situation was unexpected, bears behaving like humans. That shows a deeper level of understanding beyond just object recognition. It's picking up on context and, well, weirdness.
It's like it has a sense of what's normal and can spot deviations. That feels quite human-like.
It does, doesn't it?
These examples really drive home the potential, moving beyond the technical specs. So, as we wrap up this deep dive on VideoLLaMA 3, what are the main takeaways for you from this research?
Well, I think the big picture is that VideoLLaMA 3 really shows significant progress, a real step forward in getting AI to understand the visual world more deeply.
Through things like AVT and DiffFP.
Exactly. Through those clever innovations, AET for handling different resolutions flexibly, DiffFP for tackling video efficiently, plus that very careful approach to curating quality training data and really rigorous testing, it adds up. The model shows some impressive skills across text, images, and video. More sophisticated, more efficient.
Yeah, it really feels like these kinds of advances are paving the way for AI systems that can, genuinely perceive and interact with the world more like we do, using multiple senses or at least processing multiple kinds of input effectively.
Precisely. Which leads to a final thought, maybe something for you, the listener, to chew on. How might these specific techniques, these ways of making visual data processing more efficient and adaptable, how might they unlock completely new things? Think about robotics, for instance. A robot that can understand its visual surroundings much better, much faster.
Right, navigating complex spaces.
Or accessibility. Imagine tools for visually impaired people that can offer much richer descriptions of images or real-time scenes.
That would be incredible.
Or even creative fields.
Yeah.
How could artists or storytellers use AI that understands visuals this well to generate entirely new forms of content? These aren't just small tweaks we've talked about today. They could be building blocks for a whole new generation of AI that truly sees and understands the rich visual world around us.